general relativity, step by step. In screencast 12 I showed how a covariant vector I is expressed in the barred coordinate system according to the following transformation law. That's going to be a j, that's going to be a j, and that's going to be a bar I. And I gave an example turning from x, y space, which was Cartesian, to h, theta space, in which things are a bit more complicated because the basis vectors change. Now I'm going to show how the equivalent thing works, but for contravariant vectors. Actually, I talk about covariant, and contravariant, but I hardly use the words. I get confused as to covariant and contravariant. I normally think in terms of where the index is. Is it a downstairs index or an upstairs index? That's how I tend to think. Die x, and that's going to be Vj upstairs, summed bar I. You see how they're different rules. And I'm going to give an example again, mapping x, y to h, theta space. So what I'm going to do is consider a Cartesian space. We're going to have x and y. I'm going to call that x1 and y. No, it's going to be called x2. And the vector field I'm going to consider is going to be a nice simple constant vector field like that. Constant. I tend to think of it in terms of a flat space, a flat plane, with little things moving along it, maybe little water molecules running along in a particular direction, or little grains of dust moving along in a particular direction. I tend to think of them as movement. I tend to think of a contravariant vector field as a field of velocity. Okay, so what have we got? We've got our vector v, which is going to be equal to, that's going to be, let's say, p times ex for the horizontal component, plus qey for the vertical component. So I might write that down as V1 E1 plus V2 E2. So we're sort of getting an Einstein summation convention in here like this. Now, what happens when I start to think about it in terms of my h theta space? So that's my point, that's h, that's a right angle, that's theta. I've got h, which I'm going to call x bar 1, and I've got theta, which I'm going to call x bar 2. And what are my transformation rules? I know that h equals theta. No, I don't. I know that h equals x, and I know that theta equals arc tan of y over x. All the inverse transformations, I've got x equals h and y equals h tan theta. So what does my vector look like in this peculiar space here? Well, I've got my vector v, which is going to be equal to v bar h e h plus v bar theta e theta. And you'll remember that e h and e theta move around. They are non-constant basis vectors. They depend where in this plane you are. Okay, well, we could just resolve and take moments and stuff like that, but what I want to do is to show you how this transformation law here works for this particular case here. So let's just write it out. V bar I, in the general case, equals die x v j. That's a j, that's a bar, that's an I. So the i's are both in the upstairs position, and it's an x bar I and a v bar I. And of course this is summed over j, but I don't need to write that because we're using the Einstein summation convention, so that makes life a lot easier. Okay, v bar 1 equals what? It's let me just write it out and then I'll show you what I'm doing. It's going to be die x bar 1 by die x1 v1 plus die x bar 1 by die x2 v2. So in both cases we've got I equals 1 because it's a 1 here, which corresponds to I equals 1. And this one corresponds to j equals 1. This one, of course, is I equals 1 because I equals 1 for the whole formula, and j equals 2. And we're summing across j because of the Einstein summation convention. Equals what? X bar 1 was what? Let me just remind myself what x bar 1 was. From up here, x bar 1 was h and x bar 2 was theta. X bar 1 equals h, x bar 2 equals theta. So here we've got di h by di x. V1 in the unbarred system was just p, plus di h by di y times q equals p, because look, we know that h equals theta, no, I keep on writing that, h equals x, and theta equals arc tan of y over x. So the differential of h with respect to x is just 1, so it's times 1, I guess, times 1, plus di h dy, which is 0, times q, which equals p. Di h dy equals 0 because there's no y in that formula there. Okay, well there you go, that's quite nice. So that's v bar 1. V bar 2 equals di x bar 2, looks like a 3, 2 by di x1 v1 plus di x bar 2 by di x2 v2. So again, what we've got here is this is corresponding to I equals 2 in the general case, instead of where's my general case? There it is, there's my general case. I equals 1 I'm substituting, and we're summing through j equals 1 and 2, which is j equals 1 and j equals 2 here. Equals di x bar 2, so that's di theta, x bar 2 is equal to theta, by di x, v1 is just p, plus by di theta by di x2 is y times q. Okay, so that's equal to p times di by di x of theta, which is arc tan of y over x, plus q times di by di y of theta, which is arc tan y over x, which is that term there, equals p. Now differentiating with respect to x, it's going to be y x to the minus 2. Differential of arc tan is 1 over 1 plus x squared, so it's 1 plus y over x squared, plus, oh hang on a minute, differential, there's a minus sign there, plus q times differential with respect to y, so that's just an x minus 1 because it's multiplied by 1 over x, 1 plus y squared over x squared. Have I got the q? Yes. Equals minus py over x squared plus y squared plus qx over x squared plus y squared. Well, there it is. Those are the two components. We've got, this is going to be v bar 2, which is equal to this one, and v bar 1 was equal to p. I guess I'll write it down here again. V bar 1 equals p. Well, there it is. And again, if you start thinking about where the vectors are, what the basis vectors look like, if you've got this h theta system here, where is the vector eh? The vector eh is moving in that direction there, because you're not allowed, you're changing h from here to a little bit more, but you're not allowed to change theta. And your e theta is in the vertical direction, because you're changing theta from a little bit, from theta to theta plus delta theta, but you're not allowed to change h. And so the e theta and eh are not at right angles to one another, and they're moving around, they're non-constant vectors. So v bar 1 comma v bar 2 equals p for this one here, and then this rather peculiar term minus py over x squared plus y squared plus qx over x squared plus y squared. I guess I could tidy it up a little bit. There's a slight flaw in this problem, in this solution, which is that what I want is the vector in the barred coordinate system, and it's got x and y, which is the unbarred coordinate system. So what I want is this thing in terms of h and theta. And of course, I know that x equals h and y equals h tan theta. So I'm just going to substitute for those values there. I'll just pinch in a little bit. That's going to be p, and then it's going to be over x squared plus y squared is going to be h squared plus h squared tan squared theta Of course, this will simplify a little bit, and it's minus p times y from here, which is h tan theta, plus q times x, which is just h, equals p, and then of course that's h squared. 1 plus tan squared is sec squared theta, and I'm going to take out a factor of h, which is going to be minus p tan theta plus q, I think. And if h is not equal to 0, we've got p comma minus p tan theta plus q over h sec squared theta. And that's what my velocity field looks like in terms of the barred coordinate system, which is quite a complicated beast. I mean, this is why you use Cartesian coordinates, because we've got a very, very simple flow field, which I drew up here somewhere, constant flow field, and of course it looks dead easy in Cartesian coordinates, and it's a complicated mess in these coordinates. By design, I wanted it to be complicated because I wanted to show how non-orthogonal systems operate. And here it is. This is what the answer looks like, and it's a bit of a mess. Well, it's not a mess. It is what it is. It's just complicated. I'm going to stop there. Stop.